All right, moving on, talking more about uh, thermodynamics. And I mentioned this before about Gibbs energy before. So Gibbs is defined as H enthalpy minus T temperature times S entropy. So this was a contribution by Gibbs, and he named the variable after himself. And also, more importantly, delta G is equal to delta H minus T delta S. If delta G is negative, that means that the reaction or process is spontaneous. If delta G is positive, it means it's non-spontaneous. And if delta G is equal to zero, it's at equilibrium. And actually, Gibbs made a huge contribution to thermodynamics, and thermodynamics has benefited so much. But apparently, he himself, Gibbs, apparently was just a god awful person to be. He wasn't. He was just very awkward. He liked to sit around and do thermodynamic derivations all the time, and it made him very unpopular. And his colleagues couldn't stand him, but he just did brilliant work. And he had a mentor. The mentor's name was Lord Kelvin. I bet you can't guess who Lord Kelvin, what he did. Of course, he was involved in temperature. Okay, so, but what does this mean for this delta G? Is delta H minus T delta S and delta G being positive or negative? So I've gone here and I've made a chart. So with delta H on the y-axis, delta S on the x-axis. So in the bottom right quadrant here, so it's always spontaneous. Delta H is negative, delta S is positive. So then that T delta S term will always be negative. So in this quadrant, things are always spontaneous. Then if you look opposite for that, it's never spontaneous. If delta H is positive and delta S is negative, that means so delta H is positive, delta S is negative, so that T delta S is always going to be positive. These processes and or reactions will never be spontaneous. So what happens if you have a positive delta H and a negative delta S? If you look in the upper right quadrant, this will only work at high temperature. So these processes will only happen at high temperature. So a simple one is ice melting. So ice melting, this will only happen at high temperature because to melt ice, you need to have energy go into it. The delta H is positive. So there has to be enough entropy and temperature. The temperature and the entropy term have to be high enough to overcome that amount to make the ice melt. Then likewise, of course, low temperature. So this would be things like liquid water condensing to form solid ice. So the delta H there is negative. So when water freezes, it releases the heat of fusion. So that's negative, but entropy favors liquid water. So what happens? How will this happen if things get cold enough? When things get cold enough, then that low temperature, then that delta H will be able to overcome the T delta S term, and then the process will happen. And well, what about the third law of thermo? Or sorry, what about the second law of thermo? How is entropy increasing in these processes, especially going in the bottom left quadrant there, low temperature? Well, when you have the enthalpy being released to the surroundings, that increases the entropy of the universe. So if you're wondering how does the second law of thermodynamics hold for this, another thing about entropy, it's a state function, which means it's path independent. So if you go on into advanced calculus, that means that it's an exact differential, or it means the derivative with the partial differential of x then with respect to y is equal to the partial differential of y with respect to x, or whatever Cartesian coordinates. This is a 3D plot there for that, or whatever kind of how many dimensionality you have in that is path independent. So the things that are path independent, they are the state functions. So enthalpy, H, E, internal energy, S, entropy, G, Gibbs energy is a state function. So is A, Helmholtz free energy. That's another one we don't cover in this class. but they're exact differential, the path independent. Work and heat, though, are path dependent. So we talked about that last semester. So because of that, we can figure out the change in entropy. Just look at the entropy of the products minus the entropy of the reactants. And third law of thermo, I mentioned this before, that definition of entropy there. So let's look at some of the entropies here. So entropy of helium up to xenon. So this has to do, why is the entropy increasing for the noble gases? Well, for a given amount of energy, the more massive atoms have more closely spaced energy states. So this is interesting, and actually this is a proof for the quantization of space-time. So what we believe to be called the Planck length, that is the quantization of space-time itself. And one thing with this, so that means that things can only exist in certain areas. So space itself is quantized. There are not an infinite number of points in space-time. So, and here, in the fact that the entropy exists, it shows that the universe has structure, or I should say, space-time itself has structure. So this is interesting. It's interesting that that we have that. And imagine that space-time didn't have any structure. If that were the case, then entropy would always be infinite, because there'd be an infinite number of states. It doesn't matter. And when you deal with infinities, math gets weird, and really everything would always be infinite. So, and there would be no structure for anything with that regards. But fortunately, space-time is quantized, and we have structure to that. So remember, entropy is the number of states. So when you have a more massive atom, there are more closely spaced energy states. And if there's more closely spaced energy states, then with a given amount of area that has to work with, then there's going to be more probability of different types of states. And that's why the entropy is going up. So if you don't understand what the heck I was talking about, that's okay. It's kind of above and beyond this class, but I always thought it's kind of cool. So, but this is at the level of the class. So we have argon, nitrogen monoxide, molar mass, 40 for argon, 30 for nitrogen monoxide. Just this being stated, because the argon is more massive, you'd expect the entropy to be higher in argon, but it turns out the entropy is lower. Why is that? Well, because argon, since it's a sphere, it's just a sphere, it has only translational energy levels. So what do I mean by translational? Translational just means energy of motion, just like linear in Cartesian coordinates, the atom and or molecule flying around in space in the XYZ direction. So nitrogen monoxide, though, can also have vibrational energy levels. So the nitrogen and oxygen can store energy vibrationally. It can also have rotational, so it can spin around. So the NO can spin around with rotational energy. And because of that, it has more states. So what do I mean? So argon, so imagine that we have argon investor and nitrogen monoxide investor. And you give argon $1,000. So argon can only keep money in cash bills. Nitrogen monoxide, though, can keep money in cash, can keep money in a stock account, and keep money in a savings account. So it has 3 places it can stick its money. So the nitrogen monoxide has much more places it can place its money because it has 3 different scenarios, where argon only has 1. So because of that, the nitrogen monoxide has more entropy. So it has the translational, vibrational, and rotational, whereas argon only has translational to have entropy with that. And since things are state functions, so entropy, change in entropy for reaction is the sum of the products minus the sum of the reactants. Gibbs free energy for reaction is the sum of the products minus the sum of the reactants. And then also the standard, so the degree sign means standard delta G for the reaction is the delta H for the reaction minus the entropy change, temperature times the entropy change for the reaction. So let's do some problems with this. So this is how you can form acid rain. So there's different types, but SO2 with plus 1/2 O2 makes SO3. What is the standard Gibbs-free change of the reaction 25 degrees Celsius, and determine whether or not the reaction is spontaneous. So we have to, so the delta G is delta H minus T delta S. So we got to figure out the delta H and the delta S. So the delta H, I'll start with the delta H, is the sum of the products. So it's going to be the H SO3 minus the H of the reactant. So it's HSO2 plus 1/2 HO2. Of course, HO2 is 0. It's an element. So HSO3 is going to be minus 395.7 minus the quantity minus 296.8 plus 1/2 times 0. And if you throw that in your handy dandy calculator, you get the answer being minus 98.9 kilojoules. And do the same thing for entropy. This is going to be the entropy of SO3 minus the quantity entropy of SO2 plus 1/2 the entropy of oxygen. And entropy of SO3 is going to be 256.8 minus entropy of SO2, 248.2 plus 1/2 times 205.2, which, throw it into your handy dandy calculator, is minus 94 joules per Kelvin. 94.0 joules per Kelvin. So entropy is going down. Why is this not surprising? Because you're going from 1.5 moles of gas to 1 mole of gas. Number of moles of gas is going down. So there's something crazy going on here. And the delta G is delta H minus T delta S. So delta H is minus 98. And I always write it out. Joules minus 94 times temperature is a 298 Kelvin. Yeah, it's standard. 298. This is joules per Kelvin, and this is 298 Kelvin. And if you put that in your calculator, you get 7,900 negative 7,900 joules, or minus 70.9 kilojoules. And since it's negative, this is then spontaneous. So this reaction is negative. So determine whether or not it's spontaneous. Since it's a negative delta G, it means it's spontaneous, which means it does happen at this temperature. And we do, in fact, get sulfur dioxide reacting with oxygen to form SO3 because we have pretty bad acid rain here in Hawaii, and we get the SO2 from the volcano, right? So there we have it. All right, so why don't you try this out and see if you can figure this one out on your own. And there's some hints there. Okay, so let's talk more about some of the delta G's here. So this is the same thing with enthalpy. Enthalpy is a state function. So and these all work the same way. So if a chemical equation multiplies some factor, then G reaction is also multiplied by the same factor. If it's reversed, delta G changes sign. If a chemical reaction can be expressed as sum of series steps, then the delta G for the overall reaction is the sum of the energies for each step. And this is known as Hess's law. So this is good old Hess's law. And I think Hess's law is fun, but I think most people do not find it as much fun as I do. Okay, so let's apply this Hess's law for this this equation here. So the formation of propane. So if we take 3 carbons and 4 hydrogens, we can make propane, C3H8. I want to know what the standard Gibbs change for this chemical reaction is. I don't know what that one is, but I went to the library and I looked up the burning of stuff. So I can burn propane, I can burn carbon, I can burn hydrogen, and they were all fun to do. Right? So, but from these data, I can figure out the formation of propane from these other things. So that's the nice thing about state functions. You can do these weird experiments and figure out something that's totally different. And so one of the things I do, I just write the energy as G1, G2, G3, and keep track of it. Okay, so when I look at this, I see C3H8, and this is in the reactant side of this, and it's in the product side of the other reaction. So I'm going to go ahead and flip this equation. So I'm going to have C3CO2 plus 4 water makes 5 oxygens. That's a 5. And C3H8. So, and I flipped it, so it's minus G1. Now, carbon is where it should be. So I'm going to carbon plus O2 yields CO2. And so this is G2, and hydrogen is where it should be at. 2 hydrogens plus oxygen make 2 waters. Okay, and that's G3. Now I need to start looking at getting the proper amounts of things. So, and we're going to have to add them together. So there are 3 carbons here, and there's 1 carbon here. So what I need to do for this chemical equation is I need to multiply it by 3. Get 3 carbons, 3 oxygens, 3 CO2s, and 3 G3s that way. That's so I get the 3 carbons. And I'm going to change color to red. There's 4 hydrogens here, and there's 2 here. So what I'm going to do, multiply by 2. So I get 4 hydrogens, 2 oxygens, 4 waters, and then 2 G3s. So now let me go on and look at, now I'm going to add this together. And when I do that, notice here in black, the 4 waters cancel, the 3 CO2s cancel, and 3 plus 2 is equal to 5 oxygens, and these 5 oxygens cancel. And I'm left with 3C plus 4H2 yields C3H8, and this is minus G1 plus 3G2 plus 2G3. And another way you can look at this is to get rid of the intermediates. So if I wanted to get rid of those 4 waters and those 3 CO2s, I could look at it. That's another way I could look at doing this. So that's an alternative way of doing it. But you add them together, and you get what you originally had. That's your plot, is to get that original amount. And then you just plug in the numbers. So you get, so minus a minus, so the delta G is going to be equal minus a minus 2074 plus 3 times minus 394.4 plus 2 times a minus 457.1, and then you throw that in your handy dandy calculator and you get minus 23, and the units are kilojoules, like so. So, and that's the strategy I do. When I do this, I always put when I have equations, I put the reactants on the proper side that I want, and I put the products on the proper side I want. That's why I flipped the first equation, because C3H8 is a product, and then I leave the carbon and the hydrogen equations the same. Then I either look to get rid of intermediates, or I look to get the proper number of the reactants and or products. In this case, I look to get the proper number of reactants, and then I added the equations together, got the original one I wanted, and kept track of what I did for the equations in terms of energy. So now I add them together. In this case, I get 23 kilojoules. So this is Haas's law. You can review from last semester, but I think it's fun. It's a little puzzle. Okay, so, and you've already covered this concept last semester, so I'm not going to have a chem quiz on that. So what is things versus a reversible versus irreversible process? So if you can take imagine a piston, you have piston in a sealed container. If you really slowly remove the sand, the piston will expand. If you put it back, it'll compress. This is what I mean by reversible. So this, if you take a grain of sand off, or if you add it back on, the piston will move up and down a little bit. The truth of the matter is all processes are irreversible, but the way we get around that is just by, you can multiply a factor. The reversible times some factor gives you the irreversible process. So if you see these reversible versus irreversible processes, and this is important later on when you, if you take other classes and you see thermodynamics there. And then you have non-standard. So non-standard is when you are outside of the standard states. So the delta G reaction is non-standard. Here's another equation. It's delta G0 plus RT ln Q. Q is the reaction quotient. We talked about that back in the equilibrium chapter. So remember all the stuff that you learned before, it's coming back to haunt you. And R is gas law constant and T is temperature. So here's a graph picture showing that the free energy on the y-axis and the vapor pressure of water. Depending on where you're at, then the water will either, so it will go towards condensing or go towards evaporation, depending on where you're at in this. So if you like a picture to show something. Okay, so let's do an example of this, calculating delta G reaction in a non-standard condition. So we have this 2 nitrogen monoxide plus oxygen makes 2 nitrogen dioxides. The delta G reaction is, standard reaction is minus 71.2 kilojoules. And under the following conditions, we have these, so we'll calculate the delta G reaction using this. And is this more or less spontaneous? So the Q in this case is going to be the QP, and it's going to be the pressure of the product, NO2 squared, all the pressure of the reactant, NO squared, times pressure of the oxygen. And so we just apply this equation. So the delta G for this reaction, the delta G0, so minus 71,200. This is me. I always write this out. That's my own personal preference. Plus R, 8.314 joules per mole Kelvin. And then temperature. So we're still at 298 Kelvin. And then natural log of pressure NO, so 2 squared all over 0.1 squared times 0.1. So that's 4,000. 2 squared over 0.1 cubed, that's 4,000. But okay, then you take this and put it in your handy dandy calculator. And also the per moles is implied. It's per mole reaction if you're wondering with the units. So if you put this all in your handy dandy calculator, you will get minus 50,700 joules per mole, or minus 50.7 kilojoules per mole. Is the following more or less spontaneous? It's less spontaneous because the delta G is lower. So it's less spontaneous, but it's still proper, still done properly. And that's how you do that. So you apply the delta G. The delta G is delta G0 plus RTL and Q. And this equation is going to be important next chapter when we talk about electrochemistry as well. So if you notice with chemistry, there's scaffolding as the educational term. You have stuff that builds on previous things. So let's see if you can figure this one out and try that one out on your own. And let's go for, now another thing that's interesting, thermodynamics is tied in to the equilibrium constant. So another equation, delta G0 is equal to minus RT ln K, K being the equilibrium constant. You know what? This is absolutely amazing. This is completely amazing. Oh, and you can solve for K. K is equal to the minus delta G0 over RT. Like I'm fumbling my words. Gibbs was so instrumental in thermodynamics. Now we can tie equilibrium with thermodynamics. Thermodynamics has the energy. So if you know the energy, you know the equilibrium. And this is amazing. This is absolutely amazing that we can calculate all this stuff. This is, I mean, it's hard for me to explain. It's like this is just it's so awesome that we can do this. Can you imagine if we didn't have this? How much experience and data we'd have to carry around with us all the time, and the specialties that people would have to have for various processes. No, it's nice that we do that. This works out. Or that it's been proven for us. This is amazing. So sorry to nerd out there on that. But let's do this. Use the free energies of formation to calculate the equilibrium constant for this reaction. So, we don't even have to do this reaction. We just calculate it out. So the delta G 0 for a reaction, this is the sum of the n of the products, G of the products, minus the sum of the n of the reactants, G of the reactants. This is going to be 2GNO2 minus GN2O4 equals 2 times GNO2. So 2 times 51.3 minus 99.8. And this equals, let me find it out here, 2.8 kilojoules, 2.8 kilojoules. And then we know from rearranging the equation, K equals E to the minus delta G0 over RT. So K equals E. So to the minus delta G0 minus 2,800 joules all over 8.314 times 298 Kelvin. And that's joules per mole Kelvin. So this should be joules per mole. And 8.314 is joules per mole Kelvin. The units all balance out. And then the K of this is going to be equal to 0.32. And there you have it. So isn't this awesome? You can look up energy and you get the equilibrium constant, which is an experimentally determined thing. This is so incredible. I mean, sorry, like I said, I'm nerding out on this. I mean, it's just, saves so much time and effort and makes our lives so much easier. So thank you, Gibbs, from your grave. Okay, so recap for this one. The delta G0 is equal to minus RT ln K, which also implies that K is equal to E to the minus delta G over RT. And from that, we can take tabulated values of Gibbs free energy, and we can figure out the delta G for reaction. And from that, we can figure out the equilibrium constant. And for this one, the equilibrium constant from tabulated values is going to be 0.32. So goes about halfway. And last thing here, there's some other equations. There aren't any good examples of this in the book. But the delta G0 is equal to minus RT ln K, which also equals the delta H minus T delta S. Those are both equal to G. So you can divide both sides by minus RT, and you get that equation there. And if you want, so the ln K is minus delta H0 over R, 1 over T plus delta S over R. And then from that, you can get a 2-point equation. There's the proof for it underneath it if you want to see the proof. So it's a 2-point equation, just like it's just like you've seen before, and with the Clausius-Clapeyron equation, and then the Arrhenius equation, that 2-point equation. So you get to see this. This mental model has already been taught to you, so this shouldn't be a surprise. So, but don't worry. Pretty soon you will apply this stuff in the following chapter on electrochemistry.